So let me start. Fine. So since in the syllabus, uh, so they have designed for actually the syllabus starts at the subgroups actually, but I need to recall. So I need to recall some aspects of groups before coming to subgroups. Okay, so let me have a look at some basic concepts of groups and how it generates. So it is well known that all of you know the fact from childhood that product of two integers is again an integer. So these are basic things that you know from your childhood. So basic facts. What are the basic facts? Product of two integers is again an integer, right? So at your early stage, you didn't ask anyone that what is what, that how product of two integers will going to be another integer, but it comes to our mind naturally, right? That is, if you are given two integers a b, then their product is also in this. So this example tells you that this product, so it actually takes two integer and its value will be again an integer, right? Okay, so this example gives you an idea to formulate a basic definition of a map which satisfies the property that given any two objects, it will generate another object from the same set, right? So what would be the definition? So this can be formulated, as follows. That is, what is the definition? The definition looks like that, that given any set X, then a map dot from X cross X to X, a map dot from X cross X, since these elements are from the Cartesian product of Z, that is Z cross Z. So in general, we are considering the Cartesian product of X. So then a map dot from X cross X to X is defined to be a binary operation on the set X, right? That is, yes, on X. And you denote it by, so for any two elements, AB belongs to X. So the image dot of AB. So it looks like the functional value of this. So if you are denoting this dot by F, then actually dot AB means F of AB, right? So this is the functional value of the order pair AB. So dot AB is denoted by A dot B, right? So therefore, a binary operation on a set means it is a map, is nothing but a map from the Cartesian product of X with itself into the same set X. That is, for any two given elements AB, the image of the function will go to the set X, right? Fine. So let us have a look on some examples. Okay. So let us have a visit to some important examples. Okay. So the first one has already been cited at the beginning. This one, right? That is, given any two integer, their product is always an integer. So this product is actually a binary operation on Z. So your first example will be this one. So dot is a binary operation on Z. Fine. Right. Similarly, if you consider addition over integers, then you will find that yes, it is also a binary operation on Z, because given any two integer, if you add them, then it will be again an integer. So the addition is also a binary operation on Z. Not only that, if you consider the difference, that means given any two integer AB, A minus B, that is the difference between A and B, is again an integer. So this difference, so this is also defined by, so of AB equals to A minus B. So since for given any two integer, their difference is an integer, so this implies this is also a binary operation.
স্যার স্যার একটা কথা জিজ্ঞাসা করতে পারি?
হ্যাঁ বলো।
বলছে স্যার মাইনাসটা বাইনারি অপারেশন কি করে হতে পারে? যদি আমরা এ মাইনাস বি করি
হুম
সেক্ষেত্রে তো কোনো কোনো ক্ষেত্রে সেটা ইন্টিজার নাও হতে, ইন্টিজার মানে হচ্ছে অখণ্ড সংখ্যা। ও না না, হতে পারে হতে পারে, সরি, আমি
হুম
ইয়ে ভাবছিলাম, ন্যাচারাল নাম্বার ভাবছিলাম, সরি।
হুম হুম হুম।
হ্যাঁ,
না, না,
ঠিক আছে।
ঠিক 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 কোয়েশ্চেন করবে
হুম
অলওয়েজ।
হুম।
হুম হুম। আহ, এক সেকেন্ড দাঁড়াও তো। হ্যালো। ওকে ওকে ফাইন নাও। ওকে, okay, so the next example you can have, so you can just consider the set of all rationals. Then what will happen? Then again you will see that the operations that we have considered on Z will automatically be a binary operation on Q also, right? So the addition, multiplication, and also difference, these are also a binary operation on Q, and also on R, the set of all reals, right? And you can check that it can be extended to the set of complex, right? So these are all binary operations. Yeah, right. Now some more example can be obtained by just using your basic knowledge. That is, if you consider, just suppose that your set is the set of all reals, and consider two real numbers, a comma b belongs to R. Then what you shall get from out of these two reals? You will get two things, two reals. What are those? One is the maximum of A and B, and another one is the minimum of A and B, right? So you can define, suppose for minimum you denote the minimum as this one, that is called cap. So A cap B means minimum of A and B. As you all know that R in R you have an ordering, right, which makes R into an okay, ordered set. Yes. So actually, it is the ordering is a basically a partially ordered relation. Okay. So define A cap B as minimum of AB and A cap B as max of AB. As we have seen in R that the ordering defined on R, the usual ordering defined on R is basically it forms a lattice. That is, given any two elements, their infimum and supremum exist, right? So what are those? The infimum is the minimum of AB and the supremum is the maximum of AB. So with the help of these concepts, you can define two operations on R. And basically you have, so these two operations, this cap and cap, are both binary operations, right, on R. Now I can give you an exercise on this fact that given any lattice X, so exercise that given any lattice X, can you define two binary operations on X? Okay. Yeah. Fine. Okay. Now the next example is also an interesting one, because again we go back to the basic thing, that is to the basic facts of number theory, that given any two integer, you can always define two objects, right? What are those? That given any two integers AB, and suppose the integers are suppose they are positive, so then you can definitely have two objects out of these two integers, positive integers. What are those? One is the greatest common divisor of these two, and another one is the least common multiple of A and B, right? So on Z plus, the set of all positive integers, we can define two binary operations like the following. What are those? Sorry. Yes. For A comma B belongs to Z plus, A compose B is equal to GCD of AB, and A star B equal to LCM of AB. And I think you all know the definitions of how to calculate GCD of AB, LCM of AB, right? But by using the Euclidean algorithm. Okay. So, okay, fine. So these are all binary operations on Z plus. Okay, fine. Okay. Now again, I have already stated 6 examples, and there are many. Suppose on in 7, we can consider, suppose let us consider a power set of a set. Okay, the power set of a set X. Okay, and in this power set, you can define many operations. And what are those? And you have already seen these operations whenever you start to study set theory, that is the algebra on sets, right? So the first one was union, second one was intersection, third one was difference, and the fourth one was symmetric difference, right? Okay, and also yes, fine. So these algebra on sets, so these are actually binary operations on power set of X. So I can write down all those, that for any two subsets A B, so A union B, so the definition is it contains all those elements which are in A and B both. Either in A or in B. And the second one is the intersection, that is, it contains all those elements which are in both, that is, X belongs to A and X belongs to B. Right? So thus, given any two sets, this A union B, it generates another set. And A intersection B also generates another set. Right? Similarly, A difference B, that means it contains those elements of the set A such that which are not in B, right? And using complement, you can actually have, this one, right? Yeah. Fourth one is, it can be written as A delta B. That is symmetric difference. Okay. So what is the symmetric difference of A and B? That is, you take A minus B union B minus A. So for any two set A and B, you can define 4 binary operations on the power set of the given set X. So these are all binary operations. That is, the first one is the union. The second one is the intersection or meet. Third one is the difference. Fourth one is symmetric difference. This difference has some special property because A delta B is equal to B delta A. So that is why it is called symmetric difference. So which the ordinary difference lacks, right? It doesn't have this commutativity, because A minus B will not be equal to need not be equal to B minus A for some given sets A and B. Okay. Okay. And now we move to another example by considering the set of all M cross N matrices over, suppose, over the set of all reals, right? So now let X equals to, suppose we denote the set of all M cross N matrices over the real like that. Okay. Then what you do? So then you can define for any two matrices A and B, you can define addition. And you all know the definition of addition of two matrices. So how the addition of two matrices can be defined? Because it will be like Cij, right? What is Cij? Cij is the entry of Aij, that is the entry of the matrix A, the ij the entry of the matrix A, plus the ij the entry of the matrix B, Bij. So in this way, you can define the addition between two matrices. And this will generate another matrix of order n cross n over the real. So addition of matrices. So this plus is a binary operation, right? Binary operation on M cross N R. Okay. Now, if we consider the case for which M is equal to N, that is, if we consider the square matrices, then you can define another operation on M n cross N R. That is, if we put M equal to N, then we have that for any two matrices AB belongs to M n cross N R, the product of A and B, that is A dot B, suppose its entry will be Dij, and what is Dij? Well, Dij is, so it will look like that, summation Aik Bkj, right? K equals to 1 to N. Fine. So this is a basic definition of product of two matrices. Okay. And using this fact, so this product will generate another matrix of order n cross n. Okay. So you see that here the set of all reals doesn't put any impact, any special impact on these facts. So actually you can have all these things just if you change the set R to the set of all integers Z, the set of all rationals Q, the set of all complex numbers C, right? I'm just taking R as an example here. You do not need to put trace on this set. Just it is here for instance. Okay, fine. And there are many examples of binary operations. Okay. Now, okay. Yeah. Now, number 9 will be an important example in group theory, because it will characterize some special kind of groups which we shall see later. The groups which can be generated by a single element. So these groups can be characterized by these sets. Okay. So for this reason, we need to consider this binary operation. So you all know that on Z, if we define a relation which is denoted by this modulo some n, right? Then by the rule, yes, what is the rule? By the rule, A is congruent to B mod n. It means n divides B minus A. And with the help of this relation, you can actually partition the set into disjoint equivalence classes. And what are the disjoint equivalence classes? You will get the classes will be 0 class, 1 class, 2 class, 3 class, n minus 1 class. And how these classes will be obtained? With the help of this relation, you can just define the class A as set of all those integers x such that A is congruent to x mod n, right? Or you can write it as set of all those integers x such that n divides x minus a. That means set of all those integers x where x will take the form like this: a plus nq, q belongs to z. That means A class contains all those integers of this form, right? Okay. Now it is known to everyone that whenever you are dividing an integer by a given positive integer, suppose n, then the exact possibilities of remainders are, so the exact possible remainders are 0, 1 to n minus 1. And it can be achieved by using the division algorithm. In the division of an integer a by n, then you will have these possible remainders 0, 1 to n minus 1. And therefore, so this class, it says that whenever you are dividing the integers by n, then a class either it will contain, it will be this A will be 0, or it will be 1, or it will be 2, or it will be n minus 1. So this A class will be one of 0 class, 1 class, 2 class, n minus 1 class, right? And this says that the distinct equivalence classes of the set of all integers z quotient by the equivalence relation modulo n is the following set of equivalence classes, and this set will be denoted by Zn, and it is called, these integers are called, these classes are called the residue classes of integers modulo n. And on this Zn you can define, okay, so on Zn we define addition first, which is denoted by plus by the following way. Okay, what is the definition? So suppose let A class, B class belongs to Zn. Then what is their sum? A class plus B class. So to make it a binary operation, we need to find out one equivalence class from this, out of this equivalence classes, this, right? So how to define this? You can define this addition by this way, that is A class plus B class will be considered as A plus B class if you see that this A plus B, since it is an integer, so it is in between this 0 and n. Just take A and B, add them, and if you find that this A plus B is in 0 and n, then you just write down A plus B class, because this is your required class. Okay, but if it is not, then what will happen? Then you need to invite division by n. So you need to divide A plus B by n, and through this division you will get the required remainder, and that remainder will be in between 0 and n, and this remainder will give you the same class as that of A plus B class. That is, it is R class. What is R? R is the remainder in the division of A plus B by n. Okay, that is A plus B is congruent to R modulo n. Okay, just divide A plus B by n and you will get the remainder, and that remainder is your required class for this sum. If A plus B, if A plus B is greater or equal to n. Okay, Okay. Okay. So hence, in either case, you actually have this is equal to A plus B class. Now, what is A plus B class? You need to check that whether A plus B is in 0 and n, or it is greater or equal to n. If it is in the in between 0 and n, then it will remain as it is, A plus B class. And if it is greater or equal to n, then you need to divide this A plus B by n and just evaluate it and then get the remainder, and the remainder will give you the record class. Okay. So here, so that is, this plus is a binary operation. On Zn. In a similar manner, one can define, in a similar way, I don't want to define it again. It is, I left this as an exercise to you. So in a similar way, one can define multiplication on Zn. That is, for A class B class belongs to Zn, A class dot B class equal to AB class. Okay. And this multiplication, which says that this dot is again a binary operation on Zn. Okay. Okay, fine. Now I would like to define some aspects on binary operations which will lead to the definition of groups. So what are those? So firstly, now let us have a look on some special kind of binary operations. That means the binary operations which enjoys some property, some extra condition, right, on a set X. Okay. So the first definition is, what is that? Suppose that dot is a binary operation on a set X. Then dot is said to be associative. The binary operation is said to be associative if for any three members of the set, suppose A, B, C belongs to X, A dot B dot C is actually equal to A dot B dot C. Okay. So this property is defined to be the associativity enjoys by the binary operation dot for any three elements. And if dot is associative, associative on a set X, then one may write A dot B dot C or A dot B dot C simply like A dot B dot C without bracket. You don't need to put bracket in between two pairs of element, right? In between pairs of element, yes. So A dot B dot C, and we define okay. Yeah. Okay. We define the set X to be a semigroup with respect to the binary operation dot if dot is associative. Okay. Now I must put a note here that a set X equipped with a binary operation is defined to be a groupoid or an algebraic structure. Algebraic structure or an algebraic system. Okay. So a set X equipped with the binary operation dot, this is defined to be a groupoid or an algebraic structure or an algebraic system, which is denoted by the pair X dot. Okay. So whenever you are considering a set equipped with the binary operation dot, then you can call this pair as an algebraic system or an algebraic structure or a groupoid. Okay. Okay. Fine. Okay. So the next property is that okay. Yeah. So let us have a look on some example of semigroups. So you can easily check that, for example, Z with respect to plus, Z with respect to dot are semigroups. Similarly, R with respect to plus, R with respect to dot, C with respect to plus, C with respect to dot, Q with respect to plus, Q with respect to dot. These are all semigroups. Not only that, if you consider the last example of residue class integers modulo n, then you will find that the operations defined there, defined on Zn, that is plus and dot, these are all associative. So Zn plus Zn dot both are semigroups. Okay. So Zn plus Zn dot are all semigroups. Okay. Now one can ask that what will happen for the case if we consider the difference on the set of integers. So the difference will not be associative because a minus b minus c will not be equal to a minus b minus c. Okay. So z with respect to this difference is not a semigroup. So z with respect to minus is not a semigroup. Also, you can see that the for the case of power set, so px, so union px with respect to intersection px with respect to yes, symmetric difference. These are all semigroups. Are all examples of semigroups. So there are many examples you have come across. Yeah. Okay. Now I would like to move on to the next property. Like this. The definition is, so a binary operation dot on a set X is called commutative if for any two elements a b belongs to X, a dot b equals to b dot a. So if it is true, then you say that the binary operation dot on the set X is commutative, right? So if dot is commutative, then the algebraic system X dot is called a commutative system. Now, whenever we are dealing with groups, the groups having commutativity will be called abelian groups. So they have some special name. Okay. Okay. Fine. So, for example, of commutative system, so I just want to give you this as an exercise. The check which systems are commutative. In the list of examples. Okay. So which systems are commutative? Okay. Fine. Now, yeah. Now I move on to the next definition of a property which some binary operation on a set enjoys, which is that. Now for an example, if you consider, suppose Z plus. Now in Z plus, what you see, so one looks that in Z plus, the integer 0, it has a special kind of property, which is that the integer 0 has the property that for any integer a, if you add a to 0 or 0 to a, it will leave the same integer a plus 0, 0 plus a equal to 0. And not only that, that 0 is the only one having this property. There are no other element in Z with respect to plus which has this property, a plus 0 equal to 0 plus a equal to a. So this element is defined to be the identity of the system. Okay. Whenever you are considering this part, then you will call this 0 as the left identity. And whenever you are considering this part, then you will call this element as right identity. And if both holds, then you will call this as the identity of the system. Okay. So let us formulate this fact in the following. So generally speaking, if we consider an algebraic system, okay, an algebraic system x dot, then an element, suppose we denote it by E of x, is called, it is called, number one, left identity of x dot if E dot a equal to a or all a belongs to x, called a, sorry, yes, okay, a right identity of x dot if a dot e equal to a or all a belongs to x, and it is called an identity of x dot if both the property holds or all a belongs to x. Okay. So as an example, you can have at once that 0 in the algebraic system Z plus is the identity. If you consider multiplication over Z, then you will see that 1 is identity, because just multiply any integer with 1, you will get the same integer, right? Okay. Now, if you consider the set of all matrices, then you will find that the zero matrix will have the role of an identity. And if you consider the multiplication of matrices on the set of all square matrices over R, suppose R, then you will see that the identity matrix will be the multiplicative identity for this system. Okay? Okay, fine. Yeah. Okay. So, for example, number 1, 0 is the identity in Z plus, 1 is the identity in Z dot, 0 M cross N, the zero matrix is the identity in M cross N R, I N cross N, the identity matrix. What is the identity matrix? Whose diagonal elements are 1 and the rest are 0. So, identity matrix in M N cross N R. So, it is the identity in M cross N R dot. This is in plus. This is in dot. Yes. Okay. Yeah. Now, if you consider the residue integers modulo n, Zn, then you will see that the 0 class is the identity in Zn plus. Okay. And also 1 class is the identity in Zn dot. Okay. Fine. Okay. So, I think I should stop here today. By just introducing the definition of monoid. So, what is the definition of monoid? So, a semigroup X dot is called a monoid if it has identity. Okay. So, a semigroup is called a monoid if it has identity. Now, one can check that if a semigroup has identity, then okay, let us suppose that, so let X dot be an algebraic system and suppose it has identity. Let E1, E2 be two identities, okay? Identities of the algebraic system X dot. Then what will happen? Then E1 dot A equal to A dot E1 equal to A equal to E2 dot A equal to A dot A2, right? And this is true for all A belongs to X. So then you will see that Then now start with E1. Then what will happen? Then just put E1 for this equation. A dot E1 equal to A. Okay, this equation. Sorry. Yeah. Just put, sorry. Yeah. Yeah. Just put E1 in this equation. Then what will happen? That is, put E1 here. Then E1 equal to E2 dot E1. So it is E2 dot E1. Now if we come to the equation this, then you will see that if we put E2 here, then E2 dot E1 equal to E2. So it is E2. So this proves that in any algebraic system, if it has an identity, then that identity must be unique. Right? So therefore, in a monoid, the identity is unique. So this proves that. So this proves that in any algebraic system, x dot, if it has an identity, then it must be unique. You do not need to use the fact of associativity here. You don't need the fact associativity here. You're just using the property of binary operation, the definition of binary operation, and nothing more. So in any algebraic system x dot, if it has an identity, then it must be unique. Just by using the definition of identity and the binary operation. Okay. So in a monoid, the identity is unique. Okay. Fine. Okay. So I should stop here.